Okay, I'm going to say a bit more about the idea of chaos. So we saw that chaos occurs when you have the situation that the variables representing the state of a system remain bounded within a finite region. So they don't shoot off to infinity, they remain within certain finite bounds. But nevertheless, they follow a path that never repeats. And we said that for that to occur, you must have at least a three-dimensional phase space so that the path can cross itself without actually touching. So it crosses itself, but it's separated in the third dimension. And a classic example of that is this Lorenz curve, as we can call it, which is a representation of the evolution of the atmosphere. So this is a three-dimensional curve, a curve in three-dimensional space. The three axes aren't shown, but there are three axes corresponding to three variables that measure the state of the atmosphere, like pressure, temperature, humidity, or whatever. Then they're not that, they're more complex things, but there's three variables that represent the state of the atmosphere, and a particular point in this three-dimensional space corresponds to a particular state of the atmosphere described by those three variables. And then this curve shows how the atmosphere would evolve in this three-dimensional space, how it's those three variables, pressure, temperature, etc., would change. And what it does is it can go in a loop around one side of this diagram and then cross over to the other side and loop around there for a while and then cross back. And so it's constantly doubling back on itself like this and following these loops. And this pattern, this path, shows sensitive dependence on initial conditions because some of these lines are very close together. And so this means that you've got 2 points in this three-dimensional space which represent 2 states of the atmosphere that would seem very similar. And yet, as the atmosphere evolves, they can end up in very different places. So that's rather a surprising finding, that you'd have thought that if the atmosphere is in two different possible states that are very close, then it would remain similar thereafter. But in fact, it can be very, very close indeed, and yet go off in completely different directions. And this Lorenz curve as well is an attractor. So if we zoom in on part of it, it looks something like that. Let's say a section of the diagram there. So there are gaps in it, in this path, and if the atmosphere were to be started in this particular configuration, which is not on this Lorenz curve, then it would evolve towards it, and so eventually, you know, it would get closer and closer to it. It would take an infinite time to be exactly on it, but it would get very close to it. So this is attracting the atmosphere then into the following this particular non-repeating path. So it's a very strange kind of attractor. And one of the things then of interest is in terms of the sensitive dependence on initial conditions, just how sensitive is it? And we'll then talk about how we measure that. Okay, so this shows 2 possible trajectories that come very close to each other. So in the initial conditions, they're close, but not exactly on top of each other. So they're separated by what I've written as delta 0. At time 0, they're separated by this value delta. So that is a point at x of 0, and this is at x of 0 plus delta of 0. It's like x plus delta x. It's close to x, but it's separated by this delta of 0. And then that's our initial conditions. As the system evolves, these paths will separate because of this sensitive dependence on initial conditions. And so later on, they will be separated by a larger amount. So that should say delta of t. So at time t later, this path will have evolved to x of t, and this will have evolved to x of t plus delta of t, the difference between them at time t, which is larger than the difference at time 0. And what we find is that in the case of chaos, delta of t is related or follows an exponential growth. So it's delta 0 times e to the lambda t, where lambda is some constant. And the larger lambda, the more quickly these diverge, so the greater the sensitive dependence on initial conditions. And this lambda is known as the Lyapunov exponent. So the larger the Lyapunov exponent, the greater the sensitive dependence on initial conditions. Now we can only measure this over a certain time interval, because eventually, because the whole system is bounded, these will start to come back closer together again, or at least say will stop diverging. But so we need to look at over short timescales. But over short timescales, it will tend to diverge at an exponential rate. And so we can just measure that. We can start the system in two different states that are very close together, and then see how this delta varies over time just by evolving the two forward and taking the difference between them. And then we can plot it, and it's an exponential curve, and then we can work out what the parameter lambda here is. Now, because we have a three-dimensional system, though, there's a lambda for each of the 3 dimensions, so it may diverge in one dimension more than in others. And it could, in one dimension, rather than diverge, actually converge. It could come together, so we would have a negative exponent. So the Lyapunov exponents in the different dimensions don't have to be the same, and they could even be negative, but you do need at least one to be positive in order to create chaos, because if they're all negative, then it will just collapse and converge. But if at least one of them is negative, then at least in one dimension you're going to get sensitive dependence on initial conditions. And there's a relationship here as well to fractals. If we look back at this Lorenz curve, it has a fractal appearance, so that if we sort of look at a particular part of it, drawing this up again, we get something like that. Let's say, might be there. And then if we zoom in on this, so those 3 lines are actually something like that. There are lines within the lines. And so it looks the same as the bigger picture when we zoom in. And as we zoom in again, we'll again resolve these into finer and finer lines. So it is fractal. So it is scale-free. So there are links here to our whole scale-free phenomena of power laws and criticality. And lastly on this, I mentioned something called the logistic map. Okay, the logistic map. It's called the logistic because you can recognize this as part, what appears in the logistic equation. But instead of a differential equation, we've got a mapping, so that we calculate the new value by applying this formula to the old value. So we just take a constant r times the existing x value times 1 minus existing x value, and that gives us the new x value. So this graph shows how xn plus 1 depends upon xn. And so what we do is, if we're at xn here, we basically, with this formula, we're going up to see where we are on the curve, and that is our new xn plus 1. And then we feed that back in here, and we then go up to the curve again, and that tells us where we are now. And so then put that there, and then we go up, and we're now down here. So then feed that back in, and we're now down here. And then we go up again, and we're up here. So you can see what we've been doing is we've been jumping around this line. And it turns out that this is chaotic, and we know that because if we plot the values of xn as n increases, it swings around like that. And if we start in a slightly different place, it at first follows the same trajectory, but then it starts to go completely different. In other words, sensitive dependence on initial conditions. And also it's non-repeating. So we have the conditions for chaos. And in this case, we just have one variable, x, which we update according to this rule. So if we've got differential equations, we need at least 3 variables to produce chaos. But if we have this mapping approach, we can get chaos with just one variable. It depends on the value of r. R has to be above a certain value in order to create the chaos. It has to be less than 4, because otherwise it would start to go out beyond this. But its values close to 4 will give you this chaotic condition. So whether that is useful in socio-historical processes, maybe for some things that we might model, but it's a useful thing to know, as it's a very clear and classic example of chaos.